Hey folks, in this video we're talking about double replacement reactions, more Borks. Anywho, I would like you to be able to identify and define double replacement reactions. I'd like you to be able to predict double replacement reaction product using the solubility rules, and I would like to look at goats on things. So, double replacement reactions. This is a reaction where two ionic compounds in the aqueous state exchange their cations. So two ions that have been dissolved into water, hence aqueous state, they are mixed and then they have cations exchanging. Here's our general formula for a double replacement reaction. A and C are cations, which are always listed first. Trade places, fun stuff. So in this case, soluble ionic compounds, we need to talk about this. What is soluble? Well, soluble ionic compounds are in the aqueous state. They break apart into their individual ions. So you take a soluble ionic compound, you can put that into the aqueous state, and when you do, it breaks apart into its individual ions. So if I were talking about sodium chloride, that is actually sodium ions and chlorine ions swimming around in water. If you take some aluminum sulfate and we say that it's aqueous, well then what really is going on is we've got two aluminum ions for every molecule of this swimming around and three sulfate ions swimming around. So one or both of these aqueous compounds that we mix together, when we make these new ionic compounds and trade their cations, one of them won't stay in the aqueous state. Usually this is going to be because one of the new compounds is insoluble, meaning it cannot dissolve in water. So one insoluble product is usually what's going to happen to make a double replacement reaction go down. And this means that it's going to form a precipitate, a solid that forms and settles at the bottom of the solution. So if you mix two chemicals and suddenly combine to make one that is insoluble, it cannot dissolve in water, so it suddenly forms a solid and then kind of rains down to the bottom of the container. So an example of this would be if you took lithium bromide and you mixed that with silver nitrate. The silver bromide product that is formed is insoluble in water, and it would rain down in that container as a precipitate. So another thing that can occur is if you take two ionic compounds and mix them together, you also might perform chemistry and produce a gaseous or liquid products. So for instance, if you take acids which have an H+ ion and you combine them with a chemical that has carbonate in it, you're going to end up producing CO2 and H2O. This is what happens if you have ever done a vinegar and baking soda volcano. Vinegar is acetic acid and baking soda is a carbonate. It is sodium bicarbonate. Another example is if you took some potassium carbonate and you threw some hydrobromic acid at it. What would happen, as we talked about in acid-base reactions, is we'd form a salt from that potassium and that bromide. But the other thing that's going to occur is this hydrogen will combine with the CO3 to produce CO2 and H2O. Another thing that can occur is if you have an ammonium ion and you combine that with a hydroxide ion, it's going to produce ammonia as a liquid and water as a liquid. So an example of this would be if you took ammonium sulfate and you mix that with sodium hydroxide, you would get sodium sulfate in addition to ammonia liquid. I don't know why it says gas there. Ammonia, liquid, and water as a liquid as well. So these are double replacement reactions. But let's just keep going. So some ionic compounds, if we combine them, will not react. Just by combining two ionic compounds dissolved in water is no guarantee a reaction will occur. For instance, if you took sodium chloride and aluminum nitrate and you combine them, well, we can write that a reaction occurs, but remember how when we said everything that's aqueous is really just broken into its individual ions? Well, I can break all of these into their individual ions. On our reactant side, we're going to have 3 sodium ions, 3 chlorine ions, aluminum ion, and 3 nitrate ions. Well, on the product side, since these are both aqueous, we have the exact same thing, just written in a different order. We still have 1 aluminum ion, we still have 3 chlorine ions, we still have 3 sodium ions, we still have 3 nitrate ions. Really, nothing has changed here. There is no reaction because everything starts in the aqueous state and it all just stays the same. So since there's no changes, we don't have a reaction. So how can one possibly determine if a reaction will occur between two ionic compounds? Well, other than those gases we mentioned earlier, gas and liquid forming reactions, we're going to use these things called the solubility rules. So the solubility rules are used to determine what combinations of ions will be soluble, meaning they can dissolve in water, or insoluble, meaning they will not dissolve in water and likely form precipitates. So there's different ways to write the solubility rules, but we're going to focus on one style in my class. All right. And we're going to focus on the anion when we're looking at solubility. So if we want to figure out if a compound is soluble, we're going to first look at that anion. So let's talk about this. Anions that usually form soluble compounds include these homies right here. So if you see nitrates or acetates, which can be written in different formulas, or chloride, bromide, iodide, or sulfite, you can assume these guys are probably going to form soluble compounds, compounds that will become aqueous. Now, there are some exceptions listed here, but we'll go through those. Yeah, let's talk about them now. Nitrate has no exceptions. This means that all ionic compounds containing the nitrate ion are going to be soluble or able to form aqueous, become aqueous and dissolve in water. Ionic compounds that contain, I don't know why I didn't include acetate, but acetate compounds are also, have no exceptions, will always be soluble. Our ionic compounds, chlorine, bromine, and iodine, containing halogens, ionic compounds containing those halogens, they're going to be soluble unless we partner them with silver, the dimercury ion, or lead-2. So if you had silver chloride, AgCl, this is going to be insoluble. Or if you had lead bromide, Pb2r, that's going to be insoluble. Ionic compounds that have sulfate in them are also generally going to be soluble unless you have them mixed up with strontium ion, barium ion, and these two suspects again, the mercury and lead ions. So these dudes, if you see them, are probably going to be soluble unless they are hitting one of these exceptions. So if you see strontium sulfate, that's going to be insoluble. If you saw dimercury sulfate, that's also going to be insoluble. Let's talk about anions that are typically going to form insoluble compounds. When you see these anions in a compound, it probably will not be able to dissolve or might often form a precipitate. So if you see the sulfide anion or carbonates, phosphates, or hydroxides, these are all typically insoluble unless they're partnered with some of these exceptions. So my dude, sulfate is going to be insoluble unless you partner it with ammonium, the alkali metal cations like sodium, lithium, potassium, or calcium, strontium, and barium, a few of those alkali earth metals. Carbonate is, let's do some examples. So if you had iron sulfide, that would be insoluble. Or sodium sulfide or calcium sulfide, well, those are exceptions. Sodium is an alkali metal cation, and calcium is on our exception list, so therefore calcium sulfide is going to be soluble. Our carbonates are much less soluble. Carbonates, the face is cutting this off, but if it's alkali metal, then you're good to go. Yeah, so carbonates are insoluble unless they're with an alkali metal or ammonium. So very limited solubility on those carbonates. The phosphates, same story. We've got a magnesium carbonate is insoluble. So phosphates have the same story, and hydroxide, you can see, has its own list of exceptions. Here again, we've got calcium, strontium, and barium. Cool beans. So we can use these to predict whether or not something will be soluble. Look at this goat standing on a goat. That might be a sheep on a sheep, but still fits the thing. Goat on a turtle. We got goats on the, how many goats are in that tree? That's, you know what? I've seen a more impressive goat tree. Check out that goat tree. That's a 1, 2, 3, 4, 5, 6, 7, 8. That's a 9 goat tree. 9 goats, 1 tree. Wow, wow, wow. Anyway, let's do some practice with double replacement reactions. I would like you to use the solubility rules to determine whether or not the products from these reactions are going to be soluble or insoluble. Determine whether or not, rather, we are going to have reactions, or if these will just produce two liquids getting poured together with nothing happening. Pause the video and try it out. Yeah. Cool. You pause it out. Well, let's talk about it together. I'm going to look at these products, and here I've nicely paired them up already, and I'm going to say, are these going to form insoluble compounds? So we'll look first at the anion, and we'll say, all right, phosphate. Find that on the list. Phosphate is going to be insoluble unless it's partnered with ammonium or an alkali metal cation. That's not magnesium. Magnesium is an alkali earth metal, so this dude is going to be a solid. Meanwhile, sodium bromide, basically, if you see the alkali earth metals, you're clear. You notice that they are rather an alkali metal. If you see the alkali metals, They are always in the exceptions. So sodium bromide should be soluble. So we've got a solid and an aqueous sodium bromide. So this is a reaction. We will form a precipitate. Let's look at this next one. We've got hydroxide. OH is generally insoluble, but it's paired with an alkali metal. So potassium alkali metal, this dude's going to be soluble, aqueous. What about lithium nitrate? Well, remember, nitrate is always soluble, and lithium is an alkali metal, so this is double always soluble. So if we combine these two chemicals, no reaction is going to occur. We're just going to have mixed two chemicals. They're just going to swim around, a bunch of ions. So we're like, hey, what's up? Hey, oh, yeah, no, okay. Anyway, this next one, we're going to end up pairing silver with bromide. So let's check that. Is silver bromide going to be soluble? Well, bromine's generally soluble unless we've got silver, mercury, or lead, and we do have silver. So this is going to form a solid. Oh, and let's balance that, just like some good little beavers. And what about barium sulfate? Well, sulfate's generally soluble. Oh, unless it's partnered with barium. So this guy is going to be insoluble. It is fitting an exception to this rule. So this is going to produce two solids. There's going to be a lot of precipitate in that reaction. What about this next one? Well, we're going to pair lithium with chlorine and our OH hydroxide with iron. What about lithium chloride? Chlorines are generally soluble unless they're partnered with these dudes, which they're not. And remember, alkali metals are pretty much always soluble, and lithium's an alkali metal. So this is double good to go. That's aqueous as heck, and let's balance that out. And our iron hydroxide, well, hydroxides are generally insoluble unless they're partnered with these dudes, and iron is not one of those dudes. So this iron hydroxide will form a solid. It's iron 3 hydroxide. Anywho, that's cool. We got a reaction, no reaction, reaction, and oh wow, a reaction. Because we have solids being formed in these. Here, no solids, no changes. Anyway, that's the end of this video. I hope you understand how to predict products for double replacement reactions, and also understand how to use those solubility rules to figure out if a double replacement reaction will actually occur, or if you're just going to mix together two fun liquids. Well, ta-ta, have a great rest of your life.